All right, so here is an example problem that you might encounter something similar for the first learning objective in chapter 16. This particular example really focuses on the first part of the learning objective, which is where you're finding the different characteristics of a traveling wave. It doesn't cover how they interfere, so you would also want to review some different problems of how they interfere. And we have some examples in class that would kind of clue you into what you might have to do. So in any case, we're given an equation for this wave. Notice we are describing it with a cosine, but no big deal. Sine or cosine, it's the same thing. This is still k, the 0.4, the coefficient of x. The coefficient of t is still omega. This plus sign means that it's going from right to left. And then this is the amplitude. So the fact that it's cosine, like I said, no big deal. Okay, so I kind of wrote out all the different things that you could find. I want to try to keep everything on this page, so it might get a little cluttered. So first of all, the wave number I already showed you is 0.4, so we know that. The amplitude is the number that's out front in terms of in front of the whole expression for the cosine function. So that's 0.5, so we know that's 0.5 centimeters. The frequency, now that's the first thing. We know omega is equal to 200 inverse seconds, which is also equal to 2 pi times the frequency. So the frequency is actually equal to 200 over 2 pi. So that ends up to be 31.8 hertz is the frequency. The period is 1 over the frequency. So we just take 1 over 31.8 and we get 0.0314 seconds. The speed of propagation, so v is equal to frequency times wavelength. And when I solved this, I realized, oh, hey, I hadn't found the wavelength yet. So remember, k is 2 pi over lambda, which means that lambda is 2 pi over k. And so if we use our value for k, which is 0.4, we can find our wavelength for this wave, and it turns out to be 2 pi over 0.4, which is actually equal to 15.7 centimeters. Okay, all that to get the wavelength so we can find the speed. We have 31.8 is the frequency times our new wavelength we just found, 15.7. And we have a speed then of 499.5 centimeters per second. So that's how fast this is moving. Just a reminder, you could also find the V could be also found by taking omega over k. Remember, I discussed that in class. Now, we're asked to evaluate this function at x equals 1 centimeter and t equals 0.002 seconds. It's literally just plugging in those values for x and t. So we get 0.5 centimeters times the cosine of 0.4 times 1 plus 200 times 0.002. So it's 0.5 centimeters times the cosine of 0.4 plus 0.4. So we're taking 0.5 times the cosine of 0.8. Now, what I want to point out is that this is an angle in radians. So you have a choice here. You do have to understand that every time you see these expressions, that these angles right here are in radians. So you can take the cosine if you put your calculator into radians mode, or what I actually like to do is I change my angle, 0.8 radians. I'm going to change it into degrees. I know 180 degrees is pi radians. And so it just makes it easier. Then you never switch back the mode of your calculator and you don't screw stuff up. So the angle is 45.8 degrees. If I do put that value in to find the cosine of 45.8 and multiply it by 0.5 centimeters, I end up with 0.348 centimeters. So that's my value for y. Okay. The maximum transverse velocity of a particle, remember, the transverse velocity is the velocity in the y direction, which is the partial of the function with respect to time. For this, it would look as like minus omega a sine of kx plus omega t. I'm just trying to make it a little easier, but that is what it would generally look like if we took the derivative of that function up top there with respect to time. It's this term, so Vy max is what's out front is equal to omega times a. That's the biggest that velocity can get. And that ends up to be 100 centimeters per second. The acceleration, the transverse acceleration, is the second derivative with respect to time, which is minus omega squared a cosine kx plus omega t. So ay max is omega squared a, and that would end up to be, it's 20,000 centimeters per second squared. Okay, so I tried to kind of put in some of the other types of things we might be asked to find, like the transverse accelerations and velocities. And like I said, this problem doesn't deal with the interference. So those are also possible types of problems that you could run into.